Hello, welcome back students. A very good morning to all of you. So as you know, last class we studied about forced oscillation. Okay, in forced oscillation what we did was we externally applied an oscillating force. Okay, a time harmonic force was applied on the system and the system itself is vibrating, and we found the resultant oscillation of the system. Okay, where there was no damping from the part of the oscillator. That means velocity dependent damping was absent. Okay, so that is why we called it forced harmonic oscillator in undamped. Okay, there was no damping, so that means there was no gamma at all. Okay, and we got the response curve. Okay, applied frequency and the natural frequency of the oscillator and the relation between them we got. We also got the expression for the displacement. Okay, so we got the expression for the displacement, and we also got the differential equation of the forced oscillator. We applied actually a frequency f0, apply a force f0, and sin omega t was the time harmonic part. So this was a differential equation for a forced harmonic oscillator without any damping. Okay, undamped oscillator. And we solved the differential equation and we got the solution for the x displacement was x of t is equal to f0 by m omega 0 square minus omega square sin omega t. Okay, for what was omega 0? It was the natural frequency of the oscillator, and omega was the frequency of the applied oscillating force. And we know a capital F0 was the amplitude of the externally applied force. Okay, because the force is time varying, so we have an amplitude that was F0. Okay, and we draw the response curve. We studied the variation of amplitude of the oscillation with a different applied frequency, and we got the phenomena that when omega 0 equal to omega, the oscillations of the oscillator will be of highest amplitude. We call it resonance. Okay, we got a plot between omega and amplitude like this. Understand? Okay, so beautifully we studied all these things, and today we will move on to what is called a forced oscillator with a damping. Okay, we had an oscillator. The same system is used here. We had an oscillator. We had a x time varying x in the positive x direction and a time varying y. Okay, that is due to the applied force. We call it a y0 cos omega t or y0 sin omega t. So we know the resultant displacement of the spring will be y minus x or x minus y. That formulation or modeling we did the last time, and we had the expression. Okay, we had the corresponding expression also, and this time we have a damping. So in addition to the expression we already had, m d square x by dt square is equal to minus kx plus f0 sin omega t. This was the expression last time we had. Since here a damping is coming, a velocity dependent, a linearly dependent. Here linear dependency on velocity is implied. So okay, that is we had studied that last time. Velocity dependent damping force is given by minus dx by dt. So that was also included on the right hand side. So our resultant differential equation for the oscillator now become m d square x by dt square equal to minus kx, that is the spring force, that is also opposite, minus b dx by dt, and plus f0 sin omega t, because that is in the other way. Okay, so that is where the f plus is coming. So this is the model of the system, or the differential form of the phenomena happening inside this forced harmonic oscillator. Okay, the entire physics is represented here in this differential equation. So okay, I hope you understand it. And now, of course, what you can do next step, you can divide the entire equation with mass, so that the first term become automatically the coefficient of the first term become unity. Okay, so that is why we are dividing with the mass, the entire equation. Okay, so now we can have some substitution. We have the k by m here as usual. We can do with omega 0 square, and we have the b by m here. We can put 2 gamma, and we have the f0 by m that we can put as small f0. Okay, of course, it is understandable. F0 is Newton and small m is mass. So small f0 is unit will be Newton per kilogram. Okay, so with these three substitutions, let's move on. So when you input these values, our differential equation now become d square x by dt square is equal to minus omega 0 square, that is the natural frequency of the oscillator, minus 2 gamma dx by dt plus f0 by m sin omega t. Of course, now you can bring certain terms to the left hand side. So what happens? Our equation become d square x by dt square plus 2 gamma dx by dt plus omega 0 square x is equal to f0 sin omega t. Okay, so we got the requisite differential equation for the oscillator, which is forced as well as damped. Okay, damping is accounted with the 2 gamma dx by dt term. Okay, so this is the first part of the procedure. We set up the requisite differential equation for the harmonic oscillator, and we assume that we have a trial solution. Okay, we can either go with a complex factor, or we can go with a simple time harmonic factor. Okay, so now we select instead of complex formalism, we go for a time harmonic formalism with x is equal to a sin omega t minus theta. This is our trial solution. So what we will do next then? So we can have the dx by dt. Of course, we know when you differentiate, you get a omega cos omega t minus theta. Okay, theta is the anticipated phase difference between the applied force and the displacement. Where if they are in the same direction, then theta will be 0. If they are not in the same phase, then of course there will be a non-zero value for theta. Okay, that is the physical meaning of theta here. And again, you have to take the d square x by dt square. You can take it minus omega square sin omega t minus theta will be the second derivative of the solution. Okay, now we can input these values into the second order differential equation. So what happens? Your d square by dt square is placed with this term. Your dx by dt is placed with this term with a 2 gamma coefficient. And finally, omega 0 square x, that is a sin omega t minus theta. Okay, that is equal to the f0 sin omega t. Okay, so again, you see what we can do is we have to solve this equation. We did a mathematical manipulation. The right hand side is taken like this, so that f0 sin omega t can be written as f0 sin omega t minus theta plus theta. Okay, it makes no difference. So we have some advantage with it. Okay, again you can see now, yes, same equation here. Now what we can do, you can expand the right hand side. You have an f0. This one you can assume something like a sin a plus b form. Yes, sin a plus b is sin a cos b plus cos a sin b. Okay, so left hand side is same thing, nothing varied here, same thing, retained, all the terms are retained here, whereas the right hand side be expanded in the sin a plus b form. So we have f0 sin omega t minus theta cos theta plus f0 again cos omega t minus theta sin theta, because of the same well-known formula sin a plus b expansion. Okay, so now we have some advantage. We can correlate, add similar terms. Okay, we can correlate similar terms because we have a sin omega t minus theta here, we have a sin omega t minus theta. Of course, we have a cos omega t minus theta term here. We again have a cos omega t minus theta term. So by comparing the identical terms, okay, you can compare the identical terms. What happens? We have a sin omega, again sin omega. So of course we compared the identical terms. All the sine factors were compared. Now we can cancel all the sin omega t minus theta from LHS and RHS. So ultimately what we get minus a omega square plus A omega 0 square is equal to f0 cos theta. Okay, so some brief comparative relation. Similarly, we can compare the cosine part also. We have a cosine omega t minus theta here and here. So on comparison, on comparing these terms, what we get, cos factor we can cancel. So we get what is called 2 gamma a omega minus f0 sin theta. Okay, so some brief expressions. These boxed terms are very brief. Now we can easily solve it to get the value of a. That is our prime importance is to get the value of a, amplitude, and secondly to get the value of theta. Okay, these are the two prime important functions that we have to do. Okay, so what we can do is we can solve these relations that we got just now to get what is called amplitude. Okay, so you can rearrange it. So what we get, a into omega 0 square minus omega square f0 cos theta. Okay, now these expressions are ready for processing. You can divide both equations. So sin theta by cos theta will be a tan theta term. Understand? So divide this equation and this equation. You can divide mutually. So f0 cancel. Sin theta by cos theta will be tan theta, and you have a in the denominator and numerator. You can cancel it. So ultimately, what we get is sin theta equal to 2 gamma omega divided by omega 0 square minus omega square. Or theta will be, of course, tan inverse 2 gamma omega by omega 0 square minus omega square. So this way you got the expression for the phase factor. What is the phase difference between the applied force and the displacement? Okay, they may be in the same direction, or they may be in the same phase, or they may be in out of phase. That depends on the values of gamma, omega, omega 0 square, like that. Okay, we will look into that later. Again, now we have to solve for the amplitude. So what we can do is we can square these expressions. Which expression? This one and this one. You square it both. Okay, you square the first one, so you get like this. You square the second one, so we have a square into omega 0 square minus omega square or square is equal to f0 square cos square theta. Of course, now you can see, you have the mathematical idea that when adding these two terms, sin square and cos square will automatically vanish. Okay, so you add it. When you add, the moment you add it, you can see sin square and cos square disappear. So now we have a square into this factor plus a square into 4 gamma square omega square is equal to f0 square. Okay, so you should know that our purpose is to find the value of a. So what we will do, you take the capital A square outside, capital A square outside, so you divide it with other terms, and again when you find the a, so square root of the term will come, that will be giving you a is equal to f0 divided by square root of omega 0 square minus omega square all square plus 4 gamma square omega square. So it looks pretty confusing or complex, but in fact it has a lot of beauty. This equation carry a lot of beauty, and it has a lot of physical consequences. This expression has a lot of physical implication that we will be looking into very soon. Okay, so this is the expression for the amplitude. Okay, so now we got two important expressions. One is for the phase factor theta, one is the amplitude. So you can put all these values together in the solution. So we got the complete solution for the displacement. X is equal to f0. Okay, that we had already divided by square root of this factor times sine omega t minus theta. And the theta is what we have got now. It is nothing but tan inverse 2 gamma omega divided by omega 0 square minus omega square. So we got the solution for x. Okay, so this gives you an idea about how the displacement takes place according to force. Okay, even f0 or small f0 you can write in terms of capital F0. Okay, that is capital F0 by m. So there will be m in the denominator. Okay, so that is left for you. Now we can see that this omega is a variable. What is that? Actually, omega is the frequency of the applied force. That you can vary. And omega 0 is a constant because it is a natural frequency of the oscillator. Understand? And gamma is something related to the velocity dependent effect. Okay. So depending on this, primarily there can have three different cases. That means omega 0 can be equal to omega, or omega can be less than omega 0, or omega can be greater than omega 0. Okay, these different cases can arise. Once again, omega can be less than omega 0, or omega can be equal to omega 0, or omega can be much greater than omega 0. So this way, different cases may exist. Okay, and this is actually called the steady state solution. And there are three cases for it, depending on the value of the applied frequency. Okay, there are a large number of familiar cases happening in the nature. You can think about electrical circuits where AC voltage is applied, this frequency, external frequency, and suppose it is applied to a capacitor or an inductor, where this phenomena can happen. And at a molecular level, you can apply electromagnetic field or laser wave, laser frequency on a system or a molecule, where also this kind of displacement and applied frequency can happen. So there are innumerable number of situations in nature where this physics work out. Okay, so that you keep in mind. And now let us switch on to different cases as I mentioned. First case, I told you about a low driving frequency. That means applied frequency omega much less than omega 0. And you can have a very beautiful case of omega equal to omega 0. That means your applied frequency matches with the natural frequency of the oscillator. And thirdly, you can have a heavy driving frequency. Okay, that applied frequency much greater than the natural frequency of the oscillator. Okay, these are the three beautiful cases usually happens for such a forced oscillator. Okay, so let us go on and check into one by one. First, what is called a low driving frequency. Okay, let us see what happens. What will be the physics of the situation? Applied frequency is less than natural frequency. What will happen? We have all the ready-made equations, which all these are displayed here. We already got these relations. What happens to the theta value when this is the case? Omega is much less than means what happens? The denominator becomes simply omega 0 square. Understand? Omega 0 square, because this much less means when you subtract a small value from a big value, automatically a big value will retain. So you can see that theta can be equal to tan inverse 2 gamma omega divided by omega 0 square, because it is negligibly small as per the case. Okay, so we got the theta. And of course, since omega 0 is much larger, what happens to the ratio which is given here? This ratio becomes very, very small. That means you can imagine that this factor is tends to 0. Okay, tends to 0, very, very small. In such a condition, when theta is very, very small, okay, so what happens when that happens? The angle become very small or tends to 0. Okay, negligibly small. That means what? The phase difference between the applied force and the displacement is almost 0. That means virtually there is no phase difference. Or you can say applied force and displacement are in phase. Okay, applied force and displacement are in phase. Okay, that is what is given here. Since theta is very small, the driving force and the displacement are in the same phase. That is physics of it. Again, go for amplitude. Again, you can see amplitude. You have the denominator where you can see this factor. First term become automatically omega 0 square, because omega square is negligibly small. Okay, so this can be written like this. Why? Because this is omega 0 square and this is also very small, because omega square is very small. So ultimately what is left inside will be simply f0 divided by omega 0 square. And you know f0 is what? Small f0 is equal to capital F0 by m. Already we have assumed at the beginning. You can see that. You can go back and see in the derivation. So we get f0 by m omega 0 square. Understand? And m omega 0 square is what is called the spring constant. We already studied in one of the previous module. So we get amplitude is equal to f0 divided by k. Okay, this is the amplitude. So this is the physics. This is happening when the applied frequency is much less than the natural frequency of the oscillator. Okay, so we can conclude that the amplitude does not depend on the damping constant and depends only on the spring constant. Okay, so for low frequency case, damping constant has nothing to do. Okay, damping constant has nothing to do. Why? Because there is no velocity. Damping constant gamma is arising out of the velocity dependent damping, because velocity now frequency is very small means automatically velocity will be also very small, so damping will not arise. Velocity dependent damping will not arise. That is why a gamma is getting disappeared from the amplitude. So amplitude has nothing to do with the gamma in a low driving case. Okay, hope this idea is clear. Hope the physics is clear. Now let's move on to the resonance case. That means applied frequency and the system frequency are same. So what happens in the denominator? This becomes 0 automatically. Omega 0 minus omega becomes 0. So you can see you are dividing a term with 0 means you will get infinity. Okay, this is happening when theta is equal to pi by 2. Okay, so displacement x you can write like that. Okay, that means force and displacement are out of phase by a pi by 2 angle. That is the physical meaning. Okay, that means they are not in phase. When phase is force is maximum, a displacement may not be maximum. There will be a phase lag of pi by 2 degree. That is the meaning of this expression. Okay, so that is what is given here. It means that displacement x lags behind the driving force by pi by 2 angle. Okay, pi by 2 degree you can say. And what about the amplitude? Again, this factor will be disappearing. So what we get? We simply getting only the second term, square root of 4 gamma square omega 0 square. Automatically this becomes 2 gamma omega. So we get amplitude is equal to f0 divided by 2 gamma omega 0. Okay. So here you can see damping constant has a role. Okay. Gamma is having a role. It is coming in the denominator. So we say that gamma has a say in deciding the amplitude of the oscillator for the resonance case. Okay, so that is also clear. Now let us again move on to the third special case, when the applied frequency is much greater than the natural frequency. Understand? So in that case, what will happen to the amplitude? See here. Now omega is much greater than omega 0. That means automatically this become omega raised to 4. This is negligibly small, so omega 0 square disappear. So the first term in the denominator becomes simply omega raised to 4, and second term will be omega 4 omega square gamma square. Okay, and so see, for low damping you have the physics here. Second term can be neglected. Why? Damping is low. If damping is low and the frequency is very high, then you can write. Okay, only then you can write. Otherwise, this is the real equation. If damping is small, then gamma will be small. Second term can be cancelled or removed. So we'll have amplitude is equal to f0 divided by omega square. Okay, and omega square you can write in terms of f0 by m. So we have f0 by m omega square. Okay, so what is the conclusion here? Amplitude does not depend on force constant k. Okay, that is the conclusion. It has nothing to do with the force constant k or damping constant k. Gamma. Okay, damping constant gamma become irrelevant only when gamma is small. Otherwise, you have to take into account the gamma factor. Okay, keep in mind there is only an approximation here. Otherwise, the actual equation is this one. A is equal to f0 by root of omega raised to 4 plus 4 gamma square omega square. Okay. So, and you can see the amplitude depends on mass as well as the driving frequency. these factors. Okay, so depending on the value of omega, amplitude depends on many physical quantities. And now again you can see the what about the angle, tan theta factor. Tan theta factor we have defined. High driving frequency means omega square minus this is greater than omega 0. So in the denominator you will have a negative term. Understand? So that means you can write it as what is called is equal to minus. You can write a minus outside. So you have 2 gamma by omega. Okay, because omega cancel. So 1 omega is left here. So you have minus 2 gamma omega. So what is the meaning of this minus? Minus simply indicate that there is a phase reversal. There is a phase reversal or theta is equal to pi degree. That means in the displacement expression, a pi is coming. That means x is equal to a sine omega t minus pi is coming. So that is why we say that when the frequency of the applied frequency is very large, displacement is 180 degree out of phase with the driving force. Okay, this is the physics that we can extract from this result. Understand? Okay, and again in the previous slide you can see this can be experimented in many experiments that have been proved. When the applied frequency is much greater than the natural frequency, automatically displacement and the applied force become clearly out of phase. In many videos, if you Google out, you can see this phenomena. They are demonstrated for high frequency, high applied frequency, applied force and displacement will be actually out of phase. Okay, or 180 degree out of phase. Okay, so now let us plot certain things okay, that we have discussed so far. We have seen that as the frequency, applied frequency omega increases, amplitude become also increases from a non-zero value that is given by this term f0 by k. Again, as omega increases, you can see the case resonance when omega is equal to omega 0. When omega is equal to omega 0, resonance takes place. And again, if you increase the frequency, amplitude continuously decreases. Amplitude continuously decreases. And at some point, you can have a phase reversal also that we have seen. And okay, so this is the resonance curve or frequency response curve you can see for a forced oscillator. Okay, for different frequency, how the amplitude is, that is what is shown here. Again, suppose you plot a graph between the phase, that is theta, and the applied frequency. You can see that as the frequency increases, initially we have seen for low driving frequency, we found that phase difference is equal to pi by 2. Again, as the phase difference is omega is increased, applied frequency increased. Finally, for large frequency, we found that there will be a phase difference of around 180 degree between the applied force and displacement. Okay, this is exactly shown in this graphics. So these two graphs beautifully illustrate how the amplitude depends on omega in the first graph, and how the phase difference, phase lag depends on applied frequency omega. Okay, these two graphs are very important. So you have to understand the physics underlying behind this graph, okay, as well as the mathematics. So these graphs have been taken from your standard textbook, and I hope you understood the phenomena, physics, what we explained here, and the mathematics that we use to model the system. Okay. So if you understood, now let us move on to the assignment part. Here you have the assignment now. A very simple, beautiful question is given here. If an external periodic force f of t is equal to 50 sine 10 raised to 2t. Okay, keep in mind it is 10 raised to 2t Newton acts on a 6 kilogram mass suspended from the lower end of a spring of spring constant 150 Newton per meter. The damping force is proportional to the instantaneous speed of the mass and is 80 Newton when the speed is 2 meter per second. Find the amplitude of oscillation. Okay, so we have straightforward formula here, amplitude formula. only amplitude is asked, not the displacement. Even if displacement is asked, you can find, of course you can find the value theta. You can do in a very easy way here, because first you have to find B, okay, velocity dependent factor. You have given your force and the velocity. Your damping force is given, it is 8 Newton at a velocity 2. So definitely you can find the value B. So once you find the value B, you can definitely find the value gamma. Okay, so gamma is given. So what we can find, F0 you can easily find, because the force is given here. So K is also given. So gamma can be found, omega 0 square can be found. Omega 0 square can be found from spring constant and mass. Okay, so all these things are easily extractable from the given data. So definitely you can find the amplitude. And I suggest you that you also find the phase angle phi of this oscillator. Okay, it is not as in the problem, but still you try to find the phase angle phi. Okay, so hope you enjoy the problem. So with these few words, let us conclude, wind up today's class. Thank you all of you.